So we lead off from last lesson, which we did when we did the acceleration on an astronaut during launch. The next thing that we had to see us to consider during launch is that not just the forces on the astronaut get larger and larger, and term them in terms of G-force, but as the rocket goes up, the forward momentum of the rocket must somehow be conserved, because we know that one of the fundamental principles of physics is conservation of momentum. And so we're going to look at the conservation of momentum during launch, even though it doesn't appear that it's conserved. So, this is just two launch vehicles. You can see them here, very, very small one. This one here's got a single rocket, and this one has two booster rockets similar to the system that the shuttle uses, and a large central rocket. It doesn't matter which one, I'm just giving you some ideas of what some of the new booster rockets or the new rockets that NASA has been putting together. NASA's not the only place that launches rockets. Russia does a hell of a lot of them, and as well as the European Space Agency. But going over here, on the launch pad, just before a rocket is launched, it has no motion. Its velocity is 0. And we know that the momentum of an object, its rho symbol there, is equal to its mass times its velocity. And if the velocity is 0, then the momentum must be 0. Okay? So the sum of all the momentums at that moment is 0. Then we actually launch it into space. Now, we can't magically create momentum out of nothing. So it must be conserved. Reminding ourselves of the fundamental law of conservation of momentum. This cannot be violated. Momentum is neither created or destroyed. And the momentum in a system that exists before the system must exist as the momentum after the system. So in other words, we say the final and initial momentums of a system must be equal. And that's what we already know from this year. So having a look at this, and this is going into the work, this is actually on that, on page 25 of your blue book. We already know before the actual launch, stationary, that the momentum here must equal 0. So during launch, what is the total momentum of the system? 0. It must maintain itself. So there are two parts that must be cancelling itself out. And the first part that is cancelling is the forward motion of the rocket. So the rocket is actually moving upward. But if that is the forward motion of the rocket, there must be something that is counterbalancing this. In other words, in the opposite direction, which maintains a 0 momentum overall. And this is what it must be. The backward motion of the gases must balance out the forward motion of the rocket, so that we have this second vector of momentum being the same as the forward momentum of the rocket. Okay? So are we okay that the two motions, the forward motion and there is a backward motion, and they must be equal and opposite? So, continuing on. We're going to now have a look at, I'm going to call the mass of the rocket itself capital M, as there, and the forward velocity of the rocket capital V. So the capitalisation is for the rocket. So the rocket has forward velocity capital V and its mass is capital M. To distinguish between the mass of the gas which is spewed out the back, I'm going to use lowercase. So little m and little v. So this gas here has velocity little v, and its mass is little m. Okay? Now we know that there is zero momentum. The other thing that we must remember is momentum is a vector. So I must give a frame of reference. And I'm going to say up is positive and down is negative. So the forward momentum, the momentum in the forward direction would be m times plus v, or just plain old v. Are we okay with that? And the momentum in the backward, let's write back instead of backward, must be m, and this time it's going to be negative v because the velocity is negative. Okay. The sum of these two must equal 0. So m capital V plus little m negative v must equal 0. In other words, m capital V minus mv must equal 0, or mv equals little m little v. Are we okay with that? So the product of the mass of the rocket at any time, now remember that that's changing that big good old capital M. V, the velocity of the rocket at any time, and that's also changing at any time because we know that this rocket is accelerating at an accelerating rate. So these two values here are always changing. However, the other two on the other side, this one here, that's the mass of the gas which is being ejected out of the back, isn't it? Now, what do we know about the thrust of a rocket? It is constant. So the mass that is being spewed out the back per second is constant. Okay, when you did that worksheet over the weekend, you would have realised that there is a burn rate. How many thousands of kilograms of fuel are burnt per second? It's a constant burn rate. So that's the mass which is burnt per second. And we design the engines to push that's burnt fuel out of the rocket at a specific velocity, which gives it the thrust. So this here is also constant. So how could a capital M, capital V, where both capital M and capital V are changing, equal a constant at the back, little m, little v? Well, we know that to keep constancy, if mass goes down, what must go up to keep a constant? Velocity. And is that happening? Is as the mass of the rocket going down, the velocity increasing? Yes. And so even though this is constant, these two values here change to keep that constancy. And this is a graph that appears in your book to try and explain how this works. There is a zero level here, that's zero momentum. And the upper dotted line is the momentum of the rocket. And the momentum of the rocket increases. Okay? What is the momentum of the rocket? It's capital M times capital V, isn't it? What must occur at the same time is this line down here. What can you tell me about the shape of that upper line and the bottom line? Right, they are exactly opposite. So they are reflections in this line here. Okay. And the shape of them, I don't know what, I just copied that from the book. I don't know if it's an exact replication of what it really would look like. But if I was to, this is clear that, if I was to give you a graph which said, okay, this is a graph of the forward momentum of the rocket, then you would have to say, okay, this would be the graph of the backward momentum of the rocket. Okay? And if it was to do, if I made one here which looked like that, then you'd have to make it exactly the same. Okay? Are we Getting that idea? Okay. So here we are again, giving that a whole idea that there is this zero line. That zero line is maintained because this distance here equals that distance there. The sum of the momentum at any time, that must equal that. And that's a positive value, and that is a negative value. And that reason why that happens is simple. What? The momentum of the rocket at all time must be maintained as zero. Now, even when it's moving at a ridiculously fast rate, the momentum of that rocket still remains zero. Okay. That's the overall momentum of the rocket. Please realise that that's the rocket's forward motion plus the gases out. Okay? We also need to be able to assess the motion of the rocket in terms of Newton's third law. The poor old third law is often forgotten about. You know, for every action force there is an equal and opposite reaction force. It's the poor man's law. We forget about it. It's just, it's the ugly sister, really. She never goes to the ball. So let's make sure that we can explain the motion of the rocket in terms of the action and reaction force. And we know from Newton's third law, for every action, there must be an equal and opposite reaction force. So if F is the action force here, if that's the force pushing up, and R is the reaction force going down, then those two forces must be equal and opposite. Now, once again, to always remind everyone when you see this law. When looking like that, as you can see here, two arrows pointing up and down, people get this idea that there's overall zero force on this rocket. That is not correct. An action-reaction force pair act on different bodies. The action force is a push of the rocket on the gases. And the reaction is the gas pushing on the rocket. The two arrows act on different objects. The red one here, this acts on the gases, pushing the gases away from the rocket. And the purple one acts on the rocket, pushing the rocket away from the gas. An object which has the same force acting on it in the opposite direction would have zero overall force. This is not the same object having two forces on it. Is that clear? So even though these are equal and opposite forces, they are creating motion, one forward and one back. So let's go through, and we're now going to define a few things. Let's be capital A. Oops. Well, capital A is the acceleration of the rocket. And let's say that, go black, little a is the acceleration of the gases. Okay? Keeping with the theme of capital A is something to do with the rocket, and little a is something to do with the gases. Now, what would be the force on the rocket at any time? Well, according to Newton's second law, F equals ma. So it must be capital M, the mass of the rocket, times the acceleration of the rocket. Are we okay with that? And the reaction force is the force on the gases. What's the mass of the gas? Little m and little a. Now, what is acceleration? Now, you've all done enough calculus to know that it is the first derivative of velocity, isn't it? It's dv by dt. If not, it's velocity divided by time. Are we okay that acceleration is equal to the velocity divided by time? The change in velocity over the change in time. But later on you'll know that it's the V with the T. But who cares? So we're going to change that this here, this acceleration, this capital A, is now going to be velocity over time. Capital V, which is the velocity of the rocket, divided by the time. What time? Well, the shortest time possible, it's per second or per unit of time. Just hold that thought anyway. This is mass. What is this acceleration? It's the velocity divided by time. Velocity of what? Gas. What's the symbol for velocity of the gas? Lowercase v. Good. And it's t. But the important part is, whatever time unit I use over here has to be the same time unit over there. So 1 second, 1 second, 10 seconds, 10 seconds. It doesn't matter, it's the same time. Okay? Happy with that? If t is the same on both sides, what can we do with it? Right, it cancels. And what do we finally left again with? mv equals mv. So that's capital V, and that's lowercase v. In other words, what does this say? The forward momentum must equal the backward momentum. Yeah. Are we okay with that? So we've now used the third law to prove the two momentums of the actual rocket are the same, the forward momentum and the backward. And just to cap it off, just make sure that we understand, and I didn't put it before, the magnitude of the force must equal the magnitude of the reaction force. If we're looking at the actual force, we want to put a vector on it. This should be a minus sign here, and a minus sign there, because they're acting in opposite directions. And that gives us exactly what we needed. Okay, so there we are. We can now explain the momentum of a rocket in terms of the changing motions of the mass of the rocket itself and the gas. And we can also explain the changing momentum and motion of the rocket in terms of action and reaction forces. Okay, happy with that?